Daniel had emailed me that he had some questions. He's late getting here from his other class. Does anybody would like to raise some questions?
Sure.
Okay.
All right, 22a. Starting with like the derivative of f of x, you use the chain rule there, so it's 2 like the
so
inside and the derivative inside.
Yeah, yes. So you're talking about taking the derivative of little f?
Yeah.
You do use the chain rule.
All right, and then you have.
And then what do you do to take the derivative of little g?
You do what you did in number 20.
Right, you use number 20.
And for the chain rule part, you can have the derivative of and then the inside part there.
Mm-hmm.
So that's just like the second fundamental to calculus, right?
Actually, I usually call it the first, but yeah,
Okay.
right.
And so then you're left with
You
that
guys
other
all
part.
following this?
You're left with the inside. Rule of
Right.
the inside.
Which you don't know how to do.
Right.
Okay. So you end up with a different
Right.
strange integral to the other.
But they should equal each other somehow.
But how
So-
do you show that?
So you have an integral that is from 0 to x, and you have an integral that's from 0 to 1. Those are clearly not the same integral as they stand. What could possibly turn in an integral from 0 to 1 into an integral from 0 to x, or vice versa? What?
Changing. Oh, changing
0 to x.
No, we're down to single integrals.
Do 0 to x and x to 1, or
I mean, if someone wrote down something like integral from 0 to x of sine t, and somebody else had it as integral from 0 to 1, what would they have to have?
X. Just x. No, sine x can be.
Plug x in.
X sine t.
Really?
Let me sin x dx.
Huh?
0 to 1, then 1 to x. Right.
Sin of x.
Sine of
What if I had xt here?
And set x equal to 1.
What do you mean set x for all 1? I can't.
For all x.
That's not.
Yes.
It's supposed to be true for all x.
For all x.
So how do I make this integral look like that integral? What do I do? It's not correct as it stands, but what do you do? Use the method of wishful thinking. You mean said, make a substitution. What should I substitute? U equals xt. Where x is constant and t is your variable, right? So if I try to rewrite this in terms of u's, what would I have?
Sine of u.
And dt becomes,
0 to 1.
and u goes from
0 to x.
0 to x. So if you have an integral that goes from 0 to 1 and another integral that goes from 0 to x, they have to be related by some sort of substitution. That's the major hint, and I'm not saying any more on that problem. So this was a hint for 22. Next, sir.
For 20a,
Mm-hmm.
you give us, or, no, sorry, for 19. Yeah, you give us a hint that we should proceed with contradiction, and you give us a bunch of different problems to use from every chapter in the book.
Not quite, but yes.
Or Frenchman. But what exactly should we be, is there anything specific we should be looking to contradict?
I mean, besides following the hints, you want me to just do the problem for you?
I wouldn't be opposed to that.
I'm not going to do it.
Could you do that problem directly into factorization?
I don't know how, actually. So once you have this rectangle on which one mixed partial is bigger than the other, what should you be thinking to do?
Integrate it
Over
R, but then do it one way and then do it the other.
That's right.
But how does that look? What are you integrating one mixed partial minus the other? Right?
Or you can integrate the left-hand side of the inequality and integrate the right-hand side separately, either way.
Okay.
And what happens when you do?
It'll be 0 is greater than 0.
Right. You get a contradiction.
Can
Make
we
that
assume
point.
that if you have the integral of like f minus g is equal to the integral of f minus the integral of g?
Of course.
Okay, pretty sure.
Of course. Next. I know you had a question you said.
Well, it was mostly related to 22, so I'm gonna have to work for that.
Okay. There is a footnote on 22, making sure you justify your limit as x goes to infinity. So I wrote more on the, I added more detail with a hint than I've had in past years, so that's already enough hint. Anybody else?
When we're differentiating f, which is the square of an integral,
Mm-hmm.
we should be using chain rule there, right?
You should.
Okay.
You came in after Patrick asked that.
Okay.
Yeah. Other questions? Justin?
Integral of y minus 1 over log y. Are we supposed to do that by conventional methods? Or by conventional,
No,
I mean like
no,
use
no, no.
substitution and...
No, you can't. The whole point of this problem is this differentiation on the integral sign allows you very cleverly to compute integrals that you could never compute by putting a parameter in there, an extra variable, and differentiating under the integral sign with respect to that parameter and being able to solve. No, there's no way you can compute that integral, but you're going to, by using number 20, you're going to show that it equals log 2 by this circuitous route.
Wait, so you differentiate that whole thing and then...
Which whole thing? The capital F of x.
Right, so you're gonna compute f prime of x like it says.
You are.
And
And then you're going to see that it's something very simple. And so you actually can figure out what capital F of x is.
Oh, because you can...
If you do the derivative correctly, you'll get something very simple for what f prime of x is.
And then you can just integrate...
You can integrate that.
The
Find
derivative.
capital F of x.
Okay.
That's the, and this is actually a common technique that shows up lots of places, that you take an impossible looking problem, you make something in the problem have a parameter in it that varies, and then you differentiate with respect to that parameter and discover that you can actually say something about the harder problem that allows you to solve the easier problem.
Means you find an equivalent to this big and weird integral that's much simpler, basically.
Well, how is that integral related to capital F? Well, I even told you, it's capital F of 1.
Right.
That's how you do it. Other questions? Lama, are you asleep?
For 22 part B, when we're taking the limits of the functions f and g,
Mm-hmm.
and can we just say that the limit of f, which is the square of the limit? Can we do that
Sure.
trick?
Oh, yeah, sure. Yeah, the interesting part is dealing with G. The F part is easy. Okay. So, hearing nothing further, I want to talk about polar coordinates more today. So I want to do a couple of just straightforward computational problems, and then do something related to what we were just talking about. So evaluate the following integral. I'm going to have to cheat. I'm not going to remember this. Integral from 0 to 1, integral from x to 1, y e to the y over x squared plus y squared dy dx. Piece of cake.
Oh yeah,
Cameron's got it in his head.
you know it.
Yeah. Is there anybody that knows how to integrate that
Wolf mouth.
with respect to y?
No. I mean, not without switching the order of integration.
So you could try switching the order of integration. It would still be sort of yucky.
Five. This side. No.
I think it only gets worse if you try. All right, so you look at this problem, and even switching the order of integration does not seem appetizing, because you'd have a tangent substitution, and it's only going to get worse. However, what does the x squared plus y squared lurking in the denominator suggest?
Radial importance.
So we suggest you might try
Polar.
polar coordinates. So okay, hint, try rewriting in polar coordinates. So what should I do first?
Well, you know x squared plus y squared is r squares.
Okay, I wasn't going to do that first. What should I do first?
Map out with the integral.
We'll draw the region.
Figure out the region, right? This represents the integral over some region of this function f. What's omega?
Polar square.
Well, x goes from 0 to 1.
Y goes from x. Look at the upper half of the triangle. What's the upper triangle?
So for fixed x, y goes from x to 1. So it's going to be
In upper right triangle.
It's going to be this triangle, right? Agreed? So, in polar coordinates, what would that region look like?
Data's between pi over 2 and pi.
Fix. Theta between.
Over 4.
Theta's this angle. What's this?
Oh, sorry, pi over 4, sorry. Yeah,
Pi
yeah.
over 2.
Okay, so theta's going from pi over 4 to pi over 2. And for fixed theta, what is r doing?
It's getting longer.
Not quite.
Something like
So you can look at it in this picture. R starts at
0.
and goes to.
Some, sure. What is that?
So what's determining that? What's the equation of this line?
R sine
Y
theta
equals-
is 1.
Right, y equals 1, which means r is 1 over sine theta. So it's cosecant. And if you actually drew that in here, cosecant is going to do something like this. And you would have what for your region? You'd
Sorry.
have,
Why does y equals 1 imply r equals 1 over sine theta?
what's y in polar?
R sine theta.
Okay.
Okay, so you would have this region here, which again, you don't absolutely have to draw this to do the problem in polar. You can actually look at the picture here, but I'm just giving you some review practice here. All right, so I'm going to have the integral what? Theta goes from
Pi
What?
over 4 to pi over 2.
pi over 4 to pi over 2. For fixed theta, r goes from 0 to cosecant. And now what do I do inside? What do I put before I do anything?
R.
R.
And you used to
Remember, fudge factor. Do not forget. All right, and then I rewrite the function and I have y e to the y. Yes.
I'm sure we'll decrease this eventually.
Over r squared.
So all the r's that aren't in the e.
Everybody with us? So Cameron's noticing you have an r squared in the denominator and an r squared in the numerator, hence no r squareds left. That makes doing the integral of dr not as scary as it had been. By the way, notice this was as it stood an improper integral because the function's blowing up at the origin with the x squared plus y squared in the denominator. But as you see, when you switch it to polar, it's not really blowing up. And the polar integral is not blowing up because the r squared and the denominator get canceled out. So it's not as bad as it looks. Okay, so what do I have? I have sine theta e to the r sine theta dr d theta. Is this one your pet monkey can do?
Yeah.
I need to see this pet monkey.
It's easy. Why is it easy?
There's no r's.
And
There are no r's. Oh, wait, there is one in the
there's an r.
And divide.
Theta is constant.
Well,
But
but that's,
This is
the
just,
No,
coefficient of
forget
r.
that.
this is
Theta
just a
fixed.
simple
So it's-
derivative.
This is just what we were just talking about with substitutions a minute ago. Right? If you let u equal r sine theta, the integral of sine theta e to the r sine theta dr becomes what with du's and u's? Right. Right? The sine theta is sitting there perfectly to help you out.
Do we have to use substitution, or do we just treat it
Or you
sine
just
theta
know
as
it.
a constant?
Well, but you have to recognize that you know the antiderivative. So what is the antiderivative? It's e to the,
R sine theta.
R sine theta.
and then you put in r going from 0 to cosecant theta. Aw, isn't that cute? So what happens?
We'll get
I get e.
e minus 1.
Yeah.
E to the cosecant times sine is 1 minus e to the 0. So you have e minus 1 integrated d theta. It's a constant. So you get that times the integral of d theta from pi over 4 to pi over 2. So that was pretty easy, actually.
So do we actually have to even try to visualize these regions when we're switching to polar, or can we just,
You mean over here?
I mean, when we're making our integral and filling out the limits of,
You definitely need to draw this picture,
okay.
or else it's impossible. I mean, 90% of the time you'll mess it up if you don't draw the pictures.
Okay.
I'm saying I'm drawing these pictures, but I'm not going to force you to, and as we get into 3D and do cylindrical and spherical, I'm not going to draw these 3D pictures here. I'm just doing it to help you get used to polar coordinates at the beginning. So I'm okay if it makes you feel good to draw this picture, but I'm also okay if on this picture you label for me what theta is doing and what r is doing. I'm okay with that. Later on, we're going to do general changes of variables, and you're going to have to draw regions to get things right. Okay, next question.
Sorry, are those is y equals r sine theta, or are those the
Right.
same for whenever we do polar equations?
The mapping is given by sending r theta to r cosine theta, r sine theta. That's the polar coordinate mapping. All right. Let omega be the region bounded above by this curve and below by equals 1, let f equal y squared over the quantity x squared plus y squared to some absurd power like 5/2. Evaluate the integral of f dA over omega. So this might be some metal lamina that you built with this density function. You want to know the total mass. Okay, let's do it. Cameron's excited because he already figured this stuff out several days ago.
Yeah. You gotta complete the square on the top, make the circle.
No.
And you can.
So let's start by drawing the picture. What's the picture? Hmm?
It's a circle with its center away from the origin somewhere.
That's a little vague.
Well, completing the square would solve our problem.
Oh, that's where you meant to complete the square.
Yeah.
Or you recognize from what I've done in class,
Shifting.
it goes with the origin, right? And it's shifting it on the y-axis. So where's the center? At what height?
0,
Yeah.
radius
It's got radius 2, center 2 units high. So you can either algebraically manipulate this as we did in class last Friday and complete the square, or you can recognize that if you put in y equals 4 and x equals 0, that will solve the equation. So that tells you the top point is going to be 0, 4. So it's a circle centered at 0, 2. And remember the shortcut on finding the polar coordinates equation? Just do polar here. Or remember the picture we drew. That if this is theta, remember this is also theta. And so you have r equals some multiple of sine theta. Here's r. What's sine theta? It's r over hypotenuse, which is how long?
Not taking it.
Try 4.
But that is too.
No, r is that.
Oh, give me a circle.
All right. Now that's this guy. That's supposed to bound the curve above, and I sort of screwed up here and didn't put what I originally intended. Do I want to do? I'm going to switch this to make the problem easier. We can go back and try it. I meant to have the line through the center. Y equals 2. It's my fault. We can think about the other one in a minute if you want. But let's do this first. So I've got the line y equals 2, and the region then is
The semicircle top half.
the upper half circle, right? Half disk. Clearly I want to do this in polar coordinates, right? This is just, there's no question. So what do I have? In polar coordinates. All right, so start off and do, I don't care, you want to write the function or you want to do the limits?
Especially from
All right, what's the function?
R squared is R squared theta. Over R to the fifth.
Yes, be careful, people.
And don't forget this little r.
But be careful here not to lose track of exponents. This is r squared to the 5/2. And as Lama said, don't forget
For r.
r, and then dr d theta. Theta goes from what to what?
Pi over 4 to 3 pi over 4.
0
pi,
pi, right?
0 pi.
0 pi.
From pi over
Certainly not 0, guys.
From pi fourths to
Pi
3 pi
fourths
fourths.
to 3 pi 4.
That's right.
Yeah.
So it starts there, where, as I imagine swinging theta around, it enters the region at that value theta and then goes symmetrically over there. Is it obvious that that's pi over 4?
It's 2 up, 2 over.
2, 2. So it's pi over 4. And you're correct, it goes to 3 pi over 4. And then you go through the same game, fix an arbitrary theta in between. Where does that ray enter the region? Where does it exit?
2 cosecant theta. So
2
cosecant.
cosecant. And exits at?
4 sine theta.
Everybody with us? And in your homeworks, you're mostly doing this on web work, but get in the habit of showing your work so that on an exam I can see you didn't just memorize things, I want to actually see what you did. So remember, this is r sine theta equals 2, which means r is 2 over sine theta, and that's where Patrick got that, unless he just remembered that we just did it in the other example. All right.
Cancellation time.
Now you might want to save yourself a little work here and use symmetry. What symmetry does this problem have?
Bilateral.
Across the axis.
Right, the function I'm integrating is symmetric around the line x equals 0. Because y squared is the same here and here, and same for the denominator. So I could do what to make it a little easier?
2 times and change the.
So I could just do 1/2 of it and make my arithmetic slightly easier. It's not a huge deal. All right, let's simplify the r's here. How many? What's the net r's?
The denominator has r squared.
So I have sine squared theta over r squared dr d theta. Okay? Proceed.
Do we always want to do dr d theta? Do we ever want to do d theta dr?
That's a good question. I'm always going to write it theta on the outside because often if the region isn't just a disk centered at the origin, r is going to depend on theta. You don't want to do it the other way. Now, if we have that these limits are in fact independent of theta, then I will often, and if there's no dependence on theta here, then I will say we can just do the theta integral first and say it's 2 pi and then deal with the r integral. So that will happen in a lot of applications. But yeah, you want to be in the habit of doing it in that order because almost, if there's any interesting geometry, thetas can be the independent variable.
And yet we always draw.
Yes, I said you'd find out why in chapter 8.
All right.
All right, what do we do, guys?
Integrate.
So,
Integrates.
all right, I'll do the hard part. I'll say I'm done. All right, I'll do the next hard part. Sine squared theta.
Well,
Negative
sine squared theta over
Negative
r.
sine
No,
squared
we're doing the r.
Doing the integral dr, so the integral of dr over r squared is?
1/3 r cubed. 1/3 r cubed.
Yeah. Well, it's 1 over.
It's a
r.
negative.
No, it's
a negative.
A negative 1 over r, yeah.
R to the negative.
Yeah.
Negative r to the negative 1. Proceed.
2 integral pi over 2, pi over 4 pi over 2. Negative 4 sine theta.
Yeah.
Or no, yeah.
Huh?
Negative 1/4 sine theta.
Yeah, negative
1/4 sine theta.
Everybody agree? When you put the upper limit in, you get negative 1 over 4 sine theta, leaving 1 sine theta in the numerator.
It's going to be
Plus
1/2 sine cubed.
Sine cube. No, not 1/2.
It's just sine cubed.
Yeah, 1/2.
1/2
Sine cube.
sine squared times 1 over cosecant, which is 1 over sine. So this is sine cubed. And how gracious I was to make up a problem for you where I don't have to integrate an even power of sine. Because then you would have to do double angle formulas. I will shan't be so gracious in all of web work, so. All right, so I can do them separately. It's actually not hard to do this. I guess I want to simplify a little bit. and say it's negative 1/2 the integral of sine theta plus the integral
You mean minus?
plus the integral of sine cubed theta. So what's the integral of sine? Negative cosine, which nicely gets rid of the negative. So I have 1/2 cosine theta from pi over 4 to pi over 2. Now, how do we do integral of sine cubed?
1 minus cosine squared. U substitution.
Yeah.
So I recommend that you do scratch work on the side and then put the answer back here for bookkeeping purposes. I think it's easier that we just do an antiderivative here. And Yimeng is telling me to put in sine squared times sine. And then if you substitute 1 minus cosine squared, why would you think to do that?
Because you can't sub cosine squared.
Right, because you can integrate cosine power times sine because of the u substitution again. So we're going to get another negative cosine for integrating sine. And then I'm going to have 1/3 cosine cubed because the derivative of cosine is negative sine. So if I let u equal cosine, I have du is negative sine theta d theta. So this is u squared times du. Everybody okay? Yes? So now I'm just going to substitute that here. And of course, I could have combined this with this. So I have a net 3/2 cosine theta here, right?
Yes.
Times, so what's cosine of pi over 2? 0. What's cosine of pi over 4?
1/2.
And then plus 1/3. Cosine cubed.
There is a negative sign.
It's minus.
Oh,
It
I mean the negative.
Something's wrong.
Yeah, negative
Yeah,
cosine.
negative sign on the cosine data.
Oh,
This here?
Negative.
No, it's mean negative.
Middle.
Minus-
There.
1/3 cosine. Negative cosine.
Ah, thank you.
Where's the error?
There.
There, okay.
So I should have had negative 1/2.
That's half.
Thank you. And then cosine cubed, we're going to get negative 1 over square root of 2 cubed, which is 2 square roots of 2. So what have we got? We've got a square root of 2 in the denominator, we've got 1/2, and then we've got minus 1/6. Or I could have factored out 1/2, so this is 1/3. If you had not caught my mistake, I would have known you were wrong, because I would have gotten a negative answer, and I was integrating a positive function. Pretty good sign that I made a mistake.
What's cosine?
Right. Pretty good cosine that I made a mistake too. Everyone okay? Psyched to have fun with web work this week? All right. Famous example here.
Other than that, e to the negative x squared.
That's what I'm about to do.
Oh, okay. That we've done every way. How many ways are there to do that?
There's more, but these are the two primary ones. This function actually is very important. The e to the minus x squared function shows up all over statistics because of things called normal distributions. It shows up in probability for the same reason. It also shows up all over Fourier analysis, which is fundamental for physics and higher mathematics. So this is a very important function. However, this is famous there is no elementary antiderivative of the function e to the negative x squared.
Maybe one made up or something.
I mean, and this can actually, there's a field of mathematics called differential algebra, which is an interesting combination of Galois theory, which some of you will learn in algebra next year, or this year, with calculus. So it was actually proved early on, it's known by Liouville, for example, that you could not find a formula for an antiderivative other than just writing down the integral from 0 to x.
So what does elementary mean exactly?
In terms of elementary functions. So there's no formula for this in terms of polynomials, sines, cosines, exponentials, logs, inverse suches. And so people have defined what they call ERF. And so they will give you a tabulation of the values of ERF numerically, but there is no way to actually do anything other than to say it's ERF. However, even though I can't find an antiderivative, I can't mysteriously find the actual improper integral from 0 to infinity. You guys are doing that in number 22, but I'm going to do it a different way.
So no right.
So you'll know you're right. So, polar coordinates, what?
That's good.
How am I supposed to do polar coordinates? It's only got a single variable.
Well, there's no formula.
Okay,
No, don't look online.
Did it say
Grand trick.
Oh, we can't do this in homework?
you add another variable?
Hmm?
We can't use this for our homework?
No, 22 tells you to do it this way. So the grand trick is to say, I don't know what this is, so I'll discuss at the end why this integral makes sense, why the improper integral exists. But right now I'm just going to be engineering style and just compute. I don't know what it is, but let's just square it.
Solid.
Well, now that I've squared it, I'm multiplying a number times itself, but let's disguise one of them. Put it in a Groucho Marx nose and mustache and see what happens. And I now have a double iterated integral for this function. Right? This is a constant. This is a constant. So I can combine these into an iterated integral. If I do the first, the inside integral, I'm just holding y constant, and I've got this value times e to the minus y squared, which I then integrate from 0 to infinity. So I've now got a double integral over the infinite square here. But what mysterious important fact do you notice about this
Because
function?
it's multiplication, you can combine.
Multiplying exponentials is the same as adding exponents. That's why this grand trick works. So I have the integral over this region omega of e to the negative quantity x squared plus y squared. Now, why is this grand trick working? X squared plus y squared
R squared.
is r squared, but what comes in as a deus ex machina and saves everything?
The R.
The r fudge factor.
Oh.
That's why this
Oh, wow.
works,
Okay.
is the fudge factor. So this is going to be, in polar, the integral of e to the negative r squared r dr d theta, and that just makes everything work peachy keen. Theta goes from 0 to pi over 2, r goes from 0 to infinity, and here, Daniel, is an example where there's no theta mattering. So I might just as soon say, this is some number, independent of theta, integrate d theta, you just get pi over 2. from the theta integral, bless you, of e to the negative r squared r dr. Okay, well, so go to your scratch work.
What u equals.
Can you do this in your head?
Yeah.
U equals negative r squared, du is negative 2r dr. So what have I got? I've got r dr is negative 1/2 du e to the u. Piece of cake. So what's the answer? E to the negative r squared, right? E to the u, evaluated from 0 to infinity. Whatever that means. What does it mean to evaluate at infinity? It means take a limit as r goes to infinity, right? I'll talk about the improper integral in a second. So what have I got? I've got pi over 4, negative e to the negative big number limit.
That'd be 0.
So it goes to 0.
So
Minus negative 1/2, so that's plus 1/2, so that's giving you pi over 4. E to the negative 0. So there's the answer. So mystery number squared is pi over 4. Therefore, mystery number itself is square root of pi over 2, which is why all these square roots of pi show up all over statistics and statistical mechanics and chemistry and physics and anywhere at all that you do probabilistic modeling of things. So this is one of the great mysteries, is the square root of pi. Now, so a few words about the improper integral. So why does this even exist? Why does this make sense? And you could ask the same question here too.
It's a function area.
Why does the limit as capital N goes to infinity of the integral from 0 to n of e to the negative x squared dx exist? Yeah, so, I mean, if you graph this function, what does e to the negative x squared look like?
It's like approaching the x and y intercepts.
Huh?
No, it's approaching the x intercept, right?
X.
X
axis.
axis
Really long
one.
waterfall.
And it approaches very, very quickly.
Quicker than 1 over x squared.
Well, actually, I'd rather do something different. So if I take e to the negative x squared here, y equals, then at x equals 1, it crosses a curve that also goes to 0, but not as quickly. And that's e to the negative x. Right? X squared gets way bigger than x, so 1 over e to the x squared is much, much smaller than 1 over e to the x. But, so I can note that 1 over n, if I integrate from 1 to n here, e to the negative x squared, that's certainly less than integrating e to the negative x. Right? There's less area under a smaller height curve than there is under a larger curve. So this is, of course, comparison stuff that you guys should have all learned. And what is the integral of e to the negative x? Negative e to the negative x. So I get e to the negative 1 minus e to the negative n. So what happens as n goes to infinity? goes to 0, so this approaches 1 over e. Therefore, the area under this curve as n goes to infinity has a finite limit. What's the reason for that? That you guys all learned when you took Calc 2?
But it's less than something that has
Well, but I could have something like this that's less than something and that doesn't have a limit.
The absolute value
It's still positive. What is it that makes all these comparison test things work? It's like a squeeze principle because what?
It's bounded above by a function.
So what is it about area under the blue curve?
It's increasing.
It's an increasing function of n because the function you're getting is positive. So the key lemma that's used, whether you learned this in 2410 or Math 3100 or Calc 2, you should have seen it somewhere. If not. So what you know is that the function that integrates up to n, call that phi of n, this is an increasing function of n because the function you're taking the area under the curve of, the integrand, is always positive. So if you have an increasing function of n that's bounded above, it must an increasing,
It limits to that.
be careful, of
It
n
must converge to some value less than or equal to that.
is bounded above must converge as n goes to infinity. It needn't converge to the upper bound. In fact, it won't in our case, but it will converge to something. What's the technical way to say this so that you know it's true? What's the something to which it converges? It's the soup of the values. The least upper bound, how do you know there is a least upper bound? Well, the set of values is bounded above. So what makes all the comparison tests work is we have an increasing function that has an upper bound, in this case, given by that, so it has a limit. And for the double integral, you can play a similar game looking at squares or circles or something to see that this double integral actually exists in the proper sense. Okay. Tomorrow we're going to do cylindrical and spherical coordinates.
Yes.
No rest for the weary. So cylindrical is easy, you just throw polar into 3 dimensions. Spherical is harder, and the physicists in the room get to be confused. Oh, Michael's not here. The absent physicist in the room gets to be confused because physicists insist on using different Greek letters than mathematicians. So,
To be honest.
we're going to do that tomorrow.